Computer-generated holography has important applications in biosensing, 3D visualization, security, and many other domains. For virtual and augmented reality, holographic near-eye displays provide unique advantages of enabling true 3D projection and vision correction in a compact, eyeglass-like display. To compute a true 3D hologram for such a display, the conventional point-based method renders an RGB-Depth image for a modeled 3D scene and physically simulates light diffraction and interference for all 3D points to obtain a complex-valued hologram. This simulation, however, requires running spatially varying large kernel convolutions, and performing this for millions of points is computationally expensive even on GPUs, and currently too slow for real-time applications. This process is also performed independently for each point, and thus doesn't account for light occlusions. This causes leakage of background light for complex 3D scenes, and reduces the realism of the perceived 3D images. Recent approaches to solve these challenges include using light fields as ray-based approximations, using multilayer images to reduce depth resolution, and using low polygon meshes to replace dense point clouds. However, these approaches explicitly trade image quality with computational speed, and the demonstrated results do not provide a compelling 3D experience. To display a hologram, most existing liquid crystal-based spatial light modulators can only modulate the phase of the incident light, so we have to further convert the complex-valued hologram into a phase-only representation. One line of methods propagate the wave field iteratively between the target image and the hologram plane to update the phase pattern. These methods are typically time-consuming but produce great results for 2D images. However, no compelling results have been demonstrated for continuous 3D scenes. Direct methods such as double phase encoding rely on the observation that any normalized complex value can be represented as the sum of two phase-only values. For a complex hologram, this method decomposes it into two phase maps and interlaces them in a checkerboard pattern to produce a phase-only representation. The double phase method is instantaneous and applicable to both 2D and 3D holograms. However, it doesn't always work for complex 3D scenes and can produce severe speckle noises around high-frequency textures and occlusion boundaries. Together, the aforementioned three challenges have computationally limited the application of computer-generated holography for real-time 3D graphics applications. In this paper, we improve upon these methods and combine with deep learning to enable real-time photorealistic 3D holography. We first address occlusion modeling by reconstructing a surface mesh before diffraction simulation and detecting foreground occlusion during sub-hologram calculation. This prevents background leakage and produces a clean foreground reconstruction. To accelerate computation, we learn a convolutional neural network as a proxy of the physical simulation. The CNN learns a series of small and spatially invariant convolution kernels that progressively build different subholograms, which is orders of magnitude faster than explicitly constructing and convolving them. The nonlinear activation, such as ReLU, also stops forward propagation of occluded wavefronts, thus naturally modeling occlusion. Since the number of required convolution layers is proportional to the extent of the subhologram, we further reduce the computational cost by mapping any projection geometry to a collimated counterpart and propagating the target hologram to the center of the 3D volume to minimize the extent of the maximum subhologram. After CNN prediction, we can backpropagate the predicted hologram to any target location for the desired display configurations. To train the CNN, we need a dataset with RGB-D images and paired holograms. To learn true 3D holograms, we require the scene to be sufficiently complex and the pixel depth to be distributed uniformly across the 3D volume with no undefined depth values or depth misalignment. However, none of the existing RGB-D datasets satisfy all of these requirements, so we created a custom random scene generator. In particular, we derived a closed-form distribution for arranging meshes such that the pixel depth is statistically uniform. Altogether, we rendered 4,000 RGB-D and hologram pairs to introduce the first large-scale 3D hologram dataset, the MIT CGH4K. We use a simple, fully convolutional neural network consisting of only residual blocks and a skip connection. The model has a memory footprint of less than 1 megabyte and can easily run on mobile devices. We train the network with two losses. The first loss directly minimizes the L2 distance between the output hologram and the target hologram, with a correction that ignores the global phase offset. The second loss is a dynamic focal stack loss, which propagates the current batch to a set of focal distances that vary per training iteration, and minimizes the L1 difference between the perceived depth of field images. The trained network can faithfully predict the target hologram and reproduce high-frequency fringes in the phase map. Comparing to physical simulation, our CNN is 2 orders of magnitude faster on the GPU, and we can vary the model size to tailor for different computational devices. It further runs interactively on mobile phones by leveraging the specialized chips for CNN acceleration, which promises untethered AR/VR experience in the future. The trained CNN also generalizes to real-world scenes. Here, we demonstrate a simulated focal sweep of a real-world couch scene by refocusing the predicted hologram to different depths. Note how the different objects go in and out of focus as we sweep through the scene. Here, we show a simulated focal sweep of a 3D star test pattern consisting of varying high-frequency line pairs. The yellow circle marks the radius that is currently in focus. Note that in the center of the pattern, our hologram accurately produces the wavelength-dependent light dispersion. To encode a phase-only hologram, we show that double phase encoding fails at high-frequency regions due to the aliasing caused by the checkerboard sampling pattern and the phase wrapping that breaks the grading structure. We show that slightly pre-blurring the complex hologram before the encoding can avoid aliasing and phase wrapping, resulting in artifact-free 3D images at negligible computational cost and time. We build a simple benchtop holographic projector to validate the CNN predicted holograms. Here, the polarized laser beam is directed to the SLM by a half mirror, and the 3D image is filtered in the Fourier space and imaged by a camera. Here we show a target image and a photograph of the display side by side. Our approach allows for the creation of high-resolution, speckle-free, full-color holograms with high image fidelity. For this 3D couch hologram, we toggle between 2 photographs captured by setting the camera focus on the mouse toy and the perceptual calendar. Note how one of the magnified insets goes out of focus when the other comes into focus. We further show a live capture of the display for the green channel of the couch hologram to demonstrate true 3D projection. Here, we continuously rotate the focus ring of the camera to focus on objects at different depths. The captured results accurately match the simulation. For this Big Buck Bunny scene, we show live capture of real-time 3D hologram computation and projection. The proposed method also produces sharp and contrasting results for challenging 3D test patterns and thin text. We also captured a number of other results for rendered and real-world scenes. Please refer to our paper for more details. In conclusion, we make a step forward for computer-generated holography by combining new physically based approaches with deep learning. Our system generates photorealistic 3D holograms in real time and is robust to both rendered and captured 3D scenes. Our dataset and code are publicly available on GitHub, and we thank Sony Research Award for kindly sponsoring this project.